All right, next we would like to introduce another function. It's called a greatest integer function. Okay, and then the syntax or standard form of the function write as f of x equals int of x. Okay, int of x. Int is the abbreviation of greatest integer function. And then what this function returns? It returns greatest integer less than or equals x. Okay, so this is a very important. So if x is equals a positive number, okay, and then let's try positive integer first, and then the int of 1 is still equals that number itself. Okay, any integer, x is integer, and then returns is also the same integer, right? Because it says greater integer less than or equals x. If x equals a decimal number, and an int of 2.5 equals what? Returns greatest integer less than or equals x. So we kind of just drop the decimal point, right? Because we need this greatest integer is less than this number. So it cannot be 3. Okay, we are not doing the round off here. 2, I'm sorry. It's not doing round off, but just basically get an integer part and then drop the decimal part if x is a positive number. Okay, what if x is a negative number? If it's a negative integer and an int of -1 is still -1, it's still the integer itself. Okay, but if x is a negative decimal number, for example, and an int of -1.2 equals what? Greatest integer less than or equals this number. So that will be -2, not a -1. Okay, so be careful this greatest integer function. All right, so you can look at this table trying to see whether that makes sense to you. Okay, if x equals -1/2 and the int of x is -1, okay, not a 0, because we're looking for the greatest integer but less than this value. Okay, if it's a 0 and it's greater than this value, right, that's why it's a -1. And the same for here. So that means any number between 0 and -1, the int of x is all equals -1. Okay, any number between 0 and 1, and an int of that number will all equal 0. So if you look at a graph of greatest integer function, you will see those horizontal line segment. Okay, this little piece by piece. It's not a continuous one, okay, due to the nature of the greatest integer function. It returns only the integer. Okay, doesn't matter x is an integer or decimal, they all returns an integer. So that's why it's getting the graph like that. Okay, so actually later we're going to learn another function. It's called a piecewise-defined function. Okay, it's defined by pieces. You can look at the graph. Okay, they're all the horizontal line segment. All right. So you can use graphic calculator to graph the greatest integer function. Okay, if you use a TI-83 or 83 plus, and there's different mode you can get a graph. If you use a connected mode, and then between each horizontal line segment is use the straight line, connect adjacent one. Okay, that's why you see it's like those stairs. Okay, but if you plot, use the dot mode, and then you actually see those like a horizontal line segment. Okay, like those pieces without connect those two lines. Okay, so this is use TI-84 plus C to do the plot. All right, so greatest integer function is a piecewise-defined function. So now let's see. We formally introduce, okay, what is a piecewise-defined function and how to graph it. So let's look at an example, okay. piecewise defined function, that means the function is defined by different function, by more than one functions. Okay, that's why from graph point of view, they're put together like pieces. That's why it's called a piecewise defined function. So let's look at an example to help you to understand piecewise defined function. So f of x defines by three functions, okay, by linear function, quadratic function. So how we know, when we apply this function, when we apply this function, when we apply this function, right? It's based on the domain of the x. Okay, if x is false from -3 to +1, include -3 but not include +1. Okay, if x in that range, and then we evaluate f of x, use this linear function, -2x plus 1. If x equals 1, and then f of x equals 2, so it's like a point, okay? It's just a point. When x equals 1, y equals 2. And then when x greater than 1, and then f of x, we use square function to define. Okay, so how we evaluate piecewise defined function, we need to see the value of x falls in which subdomain. Okay, so x equals -2, for example, that falls in this subdomain, right? -2 is greater than -3, less than 1. Okay, so how to evaluate f of -2? We need to plug in to this subfunction to evaluate. Okay, so f of -2 equals -2x, right? Replace x by -2 plus 1, which is give us +4 plus 1, that equals 5. All right, and then f of 1, when x equals 1, we use the second function, right? Which is given by, that's the constant function, right? So f of 1 equals 2. And then f of 2 equals what? 2 is greater than 1, so we use this function to evaluate. That's replace x by 2, 2 squared, which is 4. What if I ask you to evaluate f of -5? If you look at a subdomain, -5 doesn't include in any of the subdomain, right? So the answer should be undefined. We cannot find any definition, for f of x, okay, because it's out of the domain. That's why we say f of 95 is undefined. All right, what about f of 0? 0 is false in the first category, right? Right here still. So that will equals what? -2 times 0 plus 1, which is still equals 1, right? So we done the A part. Determine the domain of the function. So domain of the function, we just need to combine these three subdomain into one. Okay, so let's try using the interval notation, which is easier. Okay, so this one we put -3 square brackets, right? Because here have equal sign, and then to +1, not include +1. That's why I put a parenthesis. Okay, so So this part is the interval notation for the first subdomain. And then we add the 1 in, right? Here we have x equals 1. So x can equals 1. That's why we put the square brackets here. Okay, so we have -3 to 1. And then we add in the third subdomain, x greater than 1. So we will extend, okay, here is not a 1 anymore. Greater than 1, it doesn't have any upper bound, right? So that will go to positive infinity. And infinity always parentheses. So the overall function domain is from -3 to positive infinity. Okay, so you just need to combine all the 3 subdomains into the overall domain of the function. Okay, that's the B, part B. Part C, locate any intercepts. So earlier, actually, we already evaluated f of 0 equals 1, right? So this is 0, 1, that's the y-intercept. What about x-intercept? X-intercept, we need the f of x equal to 0, right? Or y equal to 0. So we see here in the second function, f of x equals 2, so it cannot be 0, that's constant function. And then when x in the third subfunction, square function, when x greater than 1, and then x squared must be also a number greater than 1, right? So it cannot be 0. So for these two subfunctions, we cannot find the x-intercept, and only the first subfunction we can find the x-intercept. So replace f of x by 0, right? Let f of x by 0, and then 0 equals -2x plus 1, and then we're summing for the x, right? We derive 2x equals 1, and then we can easily solve x equals 1/2. So x-intercept is 1/2, 0. Okay, that's the x-intercepts. Okay, so we got a part C done. And then the D part, we want to graph the function. All right, graph the function. I need a little bit more space. All right, I'm gonna just graph over here, okay? And then just try. So first, we just have to graph each function individually, okay? Or in other words, we need to graph linear function -2x plus 1, and then graph f of x equals 2 is supposed to be a constant function, right? But the domain of x is only one value. So like I said earlier, that's just refers to a point, single point. And then the next one, quadratic function, but only part of it, right? So we have to graph those 3 parts individually.